Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at examples of subspaces. So in this topic, we're going to revisit subspaces of finite dimensional vector spaces. We'll consider a few subspaces of discrete signals and some subspaces of polynomials. All right, now given any vector space, we saw that given a finite number of vectors, if we then consider all linear combinations of these vectors, that forms a subspace of the vector space V. We're actually going to give this subspace a special name. It is the span of these M vectors. So given M vectors, the span is just simply all linear combinations of those vectors. The span of the empty set is the null vector, the zero vector. Thus, the span of a set of vectors is always a subspace of the vector space from which the vectors came. Now, in the previous topic, we also saw that the set of all polynomials of degree less than or equal to 5 also forms a subspace of the set of all polynomials in X with real coefficients. Notice that this subspace is actually equal to the span of these 6 vectors, because every polynomial of degree less than or equal to 5 is some real coefficient times 1 plus another real coefficient times x plus another real coefficient times x squared plus and so on and so forth until we have a real coefficient multiplied by x to the 5. So thus, the set of all polynomials of degree less than or equal to 5 does form a subspace of the set of all polynomials, and it is defined by this particular span. Now, in the last talk, we also saw that all vectors of the form 0, 1 plus all scalar multiples of 2, 1 did not form a subspace. After all, if I notice that if alpha is equal to 0, then 0, 1 is of that form. However, if I multiply 0, 1 by 2, I get 0, 2, and there's no alpha such that 0, 1 plus alpha times the vector 2, 1 equals the vector 0, 2. Question: do all the vectors of the form alpha times this first vector plus beta times this second vector plus this third vector define a subspace? Well, your immediate reaction may be to say no, because the above example failed. However, notice that the third vector is just a linear combination. In fact, it's just the sum of the first two vectors. So consequently, the first two vectors define a plane in R3. And the third vector is just another vector in that plane. So consequently, that the description given there does indeed define a plane in R3, although we don't really need that third vector because the plane is already well defined by the linear combination of the first two vectors. This is, of course, the xy plane. That's one significant question we're going to be answering throughout this course, and that is, when can we write one vector as a linear combination of other vectors? And that will be at least a few weeks worth of material. Now, this vector space of discrete signals includes, for example, this signal, which is powers of 2. So 1, 2, 4, 8, 16. This grows arbitrarily large. So it goes to infinity as k, or the index, goes to infinity. This one signal is not bounded. However, we will define a discrete signal x as being bounded if there exists an m greater than 0 such that the absolute value of every single entry in that discrete signal is less than or equal to m for all indices starting at 0 going to infinity. Question: is the set of all discrete signals bounded by 10 a subspace of all discrete signals? All right. So in this case, no entry in the signal can be greater than or equal to 10 in absolute value. So for this to be true, given any such signal that where every entry is less than or equal to 10 in absolute value, then alpha times x must also be bounded by 10. If this was true, given any two signals x and y that are bounded by 10, then the sum must also be bounded by 10. Now, the fact that the value 10 is fixed suggests there might be a problem here. We actually have a very simple counterexample. Consider for the example the discrete signal that simply has the value of 10 in every single entry. So the kth entry of this discrete signal is 10 for all k. Clearly, this discrete signal is bounded by 10 because every entry is less than or equal to 10 in absolute value. So this falls into the set described above. Notice, however, that 2 times this discrete signal is simply the discrete signal of all entries being the value 20. So therefore, the kth entry of 2 times the sequence of 10s is 20, and this in absolute value is greater than 10. So a scalar multiple of this discrete signal is not described by the statement above. Therefore, it is not a subspace of the vector space of all discrete signals. Question: is the set of all bounded discrete signals a subspace? So that means, given any discrete signal x, there must be an m sub x associated with it such that every single entry in absolute value is less than or equal to m sub x. Thus, given such an x, let us consider any scalar multiple of x. Well, we note that the absolute value of alpha times x at the kth index is just alpha times the kth index of x. But this is an absolute value of actually a real or complex number, doesn't matter which, and the absolute value of a product is the product of the absolute values. All right, so that's equal to the absolute value of alpha times the absolute value of the kth entry of the discrete signal x. But the kth entry is less than or equal to m in absolute value, so therefore the kth entry of alpha times x is less than or equal to the absolute value of alpha times m sub x. Therefore, given any specific alpha, alpha times x is bounded by the absolute value of alpha times m sub x. Now, alpha may be very large, 1 million, 10 million, a trillion, but it is still bounded. Also, given 2 discrete signals, x and y, there exists m sub x and m sub y such that the absolute value of the kth index of x and the kth index is less than or equal to the m sub x in absolute value, and the absolute value of the kth index of y is less than or equal to m sub y in absolute value. Therefore, the absolute value of the kth index of the sum of these two discrete signals is simply equal to the sum of the kth indices of these two discrete signals. But wait a second, we have the triangle inequality. You'll recall that the absolute value of w plus z for complex numbers or real numbers is less than or equal to the absolute value of w plus the absolute value of z. So in this case, that sum is less than or equal to the absolute value of the kth index of x plus the absolute value of the kth index of y. And the first is less than or equal to m sub x, the second is less than or equal to m sub y. Therefore, every entry in the sum of these two bounded discrete signals is also bounded. Specifically, it is bounded by m sub x plus m sub y. Therefore, the set of all bounded discrete signals is indeed a subspace. All right, now, continuing in the vector space of discrete signals, let us define capital D to the n of delta to be that discrete signal that is equal to 1 when k is equal to n and 0 otherwise. Question: what is the span of these 6 discrete signals? Now, each of these is a vector in this vector space, and therefore the span is guaranteed to be a subspace. But what specifically, or how could we verbally describe that subspace? Well, taking a look at each of these signals, we see that these are just the signals where the first, second, third, fourth, fifth, and sixth entries of the discrete signal are 1, and they are 0 everywhere else. Well, if we calculate a linear combination of these signals, then all we get is a signal that has potentially non-zero values in the first 6 entries and 0 everywhere else. Thus, the span of these 6 discrete signals is the subspace of all signals that are 0 if k is greater than 5. Now, here's another question. Consider the following definition. A discrete signal x is said to be eventually 0 if there is a capital K such that the kth index of x is 0 whenever k is greater than capital K. Does the subset of all signals that are eventually 0, does this form a subspace of the vector space of all discrete signals? Well, given x as above, if k is greater than capital K, then the value of alpha times x at index k is equal to alpha times the value of x at index k, which is equal to alpha times 0, which is 0. Thus, alpha times x is also eventually 0 if x is eventually 0. If x and y are as defined above, then there must exist capital K sub x and capital K sub y, respectively, such that the kth index of x is equal to 0 whenever k is greater than capital K sub x, and the kth index of y is 0 whenever k is greater than the capital K sub y. Let us make k be the maximum of these two values. Thus, if k is greater than the maximum of these two, then note that the discrete signal equal to the sum of these two is equal to the sum of the values of the discrete signal at this k, but because k is greater than k sub x, the first one is 0, and because k is greater than capital K sub y, the second is also 0. Therefore, this particular signal is guaranteed to be 0 after capital K, and is therefore also eventually 0. Thus, the subset of all discrete signals that are eventually 0 is indeed a subspace of the vector space of all discrete signals. Here's another quandary. Let R be any real number. So question, is the set of all polynomials that have a root specifically at R a subspace of the vector space of all polynomials in X with coefficients in the field capital F? Doesn't matter if capital F are the reals or the complex numbers in this case. Well, if P is a polynomial with a root at R, then if I multiply that polynomial by alpha, then the value of that is simply alpha times the polynomial evaluated at R. But there's a root at R, and so the polynomial evaluated at R is equal to 0, and therefore alpha times that polynomial is also going to be 0 at R. If P and Q are both polynomials with roots at R, then the sum of P plus Q evaluated at R is simply the P evaluated at R plus Q evaluated at R, but because they are both roots, therefore the polynomial P plus Q is also 0 at R. Thus, this is indeed a subspace. Here's a similar but subtly different question. Let R be a real number. Is the set of all polynomials such that P at R is equal to 1 a subspace of the vector space of all polynomials in X with coefficients in the field capital F? Well, if P is any such polynomial, then P at R is equal to 1. But consequently, if I multiply that polynomial by 2, then twice the polynomial evaluated at R is just twice that polynomial evaluated at R, which is just equal to 2 times 1, which is 2. So therefore, if P falls into this category, 2 times P does not. Therefore, this set of polynomials is not closed under scalar multiplication and is therefore not a subspace of the set or the vector space of all polynomials. All right. Following this topic, you now have a better understanding of the idea of a subspace. Now, for finite dimensional vectors, I have already made the claim that all subspaces are the span of some set of vectors. However, I have also now shown you, and you've seen, a number of subspaces of discrete signals, and in some cases you should be able to notice that it may not be possible to describe some of those subspaces as being spans of only a finite set of vectors. Similarly, you've seen a number of subspaces of the vector space of all polynomials in X with either real or complex coefficients. Here's the references, acknowledgements, the colophon, and the disclaimer. Cheers!